Hi, in this video, we're going to talk about Taylor and McLaurin series. Taylor and McLaurin series are extremely similar. In fact, McLaurin series are a special case of Taylor series. Let's talk about Taylor series first. So a Taylor series Taylor series has two pieces that are important to determining what it looks like. The first is going to be the function that we're looking to approximate or represent. Because if you have a Taylor series, it can actually represent the entire function. The second thing is A, which is a number where we want to center our series. So the big idea is that if we have these two pieces, then we can define the Taylor series as the sum from n equals 0 to infinity of the nth derivative of a over n factorial times x minus a raised to the n. Now, before we go any further with this, we've given the things you need to find a Taylor series, and we've given the formula for the Taylor series. I want to add a bit more information, frameworks that might be helpful. So the first is, remember Taylor polynomials. Taylor polynomials were used to approximate a function at a particular value. And you can think of Taylor series as infinite Taylor polynomials. If you look at the formula, what you'll see is this is a Taylor polynomial formula. It's just that I never stop. I used n here, and I want to change that to k because we used n for the degree earlier. It doesn't matter, r or t, whatever the variable is. The other thing to recognize about Taylor series is that they are a special type of power series. So power series are something we saw a bit ago where we had some kind of coefficient on each of the powers of x, and these could be used to represent functions. And it's just that in a Taylor series, we have a very special formula, and we're not necessarily going to have to use x. So we're going to use x minus a if we want to change where this is centered. So my coefficient comes from evaluating the kth derivative at a and taking k factorial, dividing it by k factorial. And I'm allowed to use x minus a, which could algebraically be rewritten to use x minus a. Could be algebraically rewritten to just use x to the k. So these are two important ways of thinking about Taylor series. So let's look at an example. Let's see, what is the Taylor series for f of x equals e to the x at x equals 0. Now to find the Taylor series expansion, we're given the function we want and the value that we want to center at. So what I need to do is I need to find what is f of 0. My first coefficient will be f of 0 divided by 0 factorial. So this is e to the 0 divided by 0 factorial, 1 over 1, which is 1. So I'm going to start with 1 as my first term. Now I'm going to look at my second coefficient, which will be c1 is f prime of 0. Now I'm using that first derivative divided by 1 factorial. Now the important thing to remember here is that my f of x is equal to e to the x. So f prime of x is equal to e to the x, f double prime of x is equal to e to the x. All of my higher derivatives are going to be equal to e to the x. So f prime of 0 over 1 factorial is 1 over 1, which is awesome. So that's going to be my coefficient on x. Then for x squared, I'm going to look at f double prime of 0 over 2 factorial, which will be 1 over 2. So my next term is 1/2 x squared. So far, so good. But I don't want to write this out forever. What I need is a pattern that enables me to express this in terms of any value of k, because I'm not going to be able to sit here and write out infinitely many terms. So what I need to recognize is, how do I get to an arbitrary c sub k? Well, that's going to be the kth derivative of x with 0 plugged in divided by k factorial. And because the kth derivative of e to the x is always e to the x, the kth derivative of x with 0 plugged in, the kth derivative of f of x with 0 plugged in will just be 1. So on every term, coefficient on c sub k, the coefficient on x raised to the k will always be 1 over k factorial. So the Taylor series expansion for f of x equals e to the x at x equals 0 is the sum from k equals 0 to infinity of 1 over k factorial times x to the k.